In this video, I'm going to be explaining how to use implicit differentiation. First thing we want to do is figure out what it means to be in an implicit form. So there's two types of forms equations or functions can be in. Explicit forms are where functions are written explicitly for one variable, like y equals something. Implicit forms means that we haven't solved for a single variable. So these are actually the same function or the same equation. This is written in implicit form. We just multiplied both sides by x. This is written in an explicit form. So a lot of times we've been deriving in an explicit form, although we can actually derive it in an implicit form by using the following strategies. Sometimes, however, even solving in an explicit form is really difficult or even impossible. This is an example where solving for this explicitly is very difficult, if not impossible. And so that wouldn't be worth our time to do. We just want to be able to find the derivative or find the slope of this curve at any point. So we can just derive it implicitly. So the way to derive it implicitly, first of all, is to think about what it means to derive a different variable with respect to x. If we derive an x term with respect to x, that's our derivative rules that we're used to. If I try and derive a different variable with respect to x, I got to think about that as using the chain rule. So if we think about y is the output of a function depending on whatever the input is, then we can look at that as a chain rule. Whatever I plug in determines what my output is. So if we think about deriving y using a chain rule, we could follow the following steps. If I derive y with respect to x, that's the same as deriving y with respect to y times the derivative of y with respect to x. So if I derive y squared with respect to y, that's just 2y. And if I times that by the derivative of y with respect to x, well, dy dx is the same as y prime. So I'm just changing the symbol even though they represent the same thing. The easiest way to think about this is anytime you derive a variable that is not x, use your normal derivative rules and then just attach the derivative of that variable to the end of it. So when we use implicit differentiation, we're going to derive each term individually with respect to x. We're going to try and solve for y, so we're going to gather all of our terms that have y prime in them so that we can factor that out and solve for y prime. Let's see how that works. Here's our first example, 3x plus y equals 0. So rather than solve for y and find its derivative, I'm going to derive it as it is right now implicitly. I'm going to derive each term individually. So the derivative of 3x with respect to x is just 3. But the derivative of y with respect to x is the derivative of y. And you can keep it in this form, dy over dx, that represents the derivative of y. I think it's easier when we're doing implicit differentiation to use this symbol instead, y prime. It's just a little bit easier to work with than this fraction. So now that we have 3 plus the derivative of y equals 0, we can solve for the derivative of y by just subtracting 3 from both sides. And so the derivative of y with respect to x is negative 3. And we already knew that. If we subtracted 3x from both sides and found the derivative of negative 3x, we would get negative 3. However, you'll see in the following examples that solving explicitly is not so easy, and we want to be able to get better at differentiating implicitly. So let's use that on this next example. To derive x squared plus y cubed equals 2, I'm going to derive each term individually with respect to x. So the derivative of x squared with respect to x is 2x. The derivative of y cubed with respect to x is 3y squared times the derivative of y. So the derivative of this is the normal rules with the derivative of that variable attached to the end. And the derivative of 2 is 0. So now I want to solve for y prime. I'm going to subtract both sides by 2x or move 2x to the other side. And then I'm going to divide both sides by 3y squared. So the derivative of y with respect to x is negative 2x divided by 3y squared. And if I had coordinates, if I had an x and a y coordinate, I could plug those in, and I could find the slope or the derivative at that point. We'll do that in the next video. Let's keep practicing deriving implicitly. So here's an example for x minus the cosine of y equals 1. Derive each of these terms individually with respect to x. So the derivative of 4x with respect to x is 4. The derivative of cosine of y with respect to x is negative sine of y times the derivative of y. And since we're subtracting that quantity, we want to distribute that negative. So we get positive sine of y times the derivative, or times the opposite of the derivative of y. We're distributing that negative throughout here. And then I subtracted 4 from both sides, so I put negative 4 on the other side. Now I just have to divide both sides by sine of y, but that gives me the opposite of the derivative of y equals negative 4 over the sine of y. So the opposite of that would be positive 4 over the sine of y, or you could think that we multiply both sides by negative 1. In this example, we're going to see how we can use other differentiation rules like the product rule to find derivatives implicitly. It's not going to change our process. We're still going to use the product rule like we know it. So if I derive x times y squared with respect to x, I use my product rule and I find the derivative of the first term times the original second plus the original first terms times the derivative of the second. So the derivative of y squared with respect to x is going to be 2y times the derivative of y. So now I want to solve for y prime. I'm going to take that y squared, move that over to the other side, it becomes negative, and then I'm going to divide both sides by 2xy. So the derivative is negative y squared over 2xy, and then I can simplify the y's here and write my simplified derivative, which is negative y divided by 2x. One more example. Let's see if we can handle this one. So again, we're deriving implicitly. We're going to derive each term individually with respect to x. So the derivative of y to the fifth with respect to x is 5y to the fourth times the derivative of y. The derivative of x squared times y cubed means that I got to use my product rule. So the derivative of x squared is 2x times the original second function, y cubed, plus the original first function, x squared, times the derivative of the second. So the derivative of y cubed is 3y squared times y prime, because we're doing it with respect to x. On the other side, the derivative of 2 with respect to x is 0, and the derivative of x squared times y is going to require the product rule once again. So the derivative of x squared is 2x times the original second function, y, plus the original first function, x squared, times the derivative of the second, and the derivative of y is the derivative of y prime. So let's clean up this mess a little bit. Nothing is being distributed to anything in here, so we can get rid of all of our parentheses and brackets and organize some of our variables in alphabetical order. So my first term stayed the same, 5 times y to the fourth times y prime. This I pulled out of here, so I just reorganized it, put the 3 at the front, and then x squared, and y prime at the back. And this I joined together and became 2xy cubed. On the other side, I just brought this together, 2xy, and x squared y prime right there. So now I want to organize and get all my y primes on the same side. I'm going to put them on the left side, although it doesn't matter. So here I have a term with y prime, I'm going to keep that there. Here I have a term with y prime, I'm going to keep that there. But I want to move this term to the other side, so I'm going to subtract that from both sides. It's negative 2xy cubed on the other side. And then I want to move this term, x squared y prime, to the other side, so it's negative over there. Now that I have all three terms with y prime in them, I can factor out that y prime. And that leaves behind this. And now I can just divide both sides by that entire quantity, and we got our final derivative with respect to x. So there's an introduction to implicit differentiation.